we're going to talk about Cramer's rule, which is another way to solve systems of equations using matrices. They involve what's called a determinant, which notation-wise can be det with a, or what looks like absolute value of capital letter, but it is not absolute value. It's just those two vertical bars with the letter representing your matrix inside. How you calculate it is just multiply, for a 2 by 2 matrix at least, just multiply your diagonals. So you take top left to lower right hand corner, a times d, minus upper right to lower left corner, b times c. For the determinant of our matrix in our first example, I'm going to go ahead and switch it so it actually has the notation that says, hey, find the determinant. So my vertical bars say find the determinant of this. And then you'd multiply 6 times -4 minus your other diagonal, -2 times +1. And you're going to end up with, that's -24 plus 2, -22. How you use these determinants to find a solution to a system of equations in Cramer's rule is you basically set up two different matrices and divide their determinants. So how it works is it looks very, very complicated, but your denominator for finding both variables is the same. It's your coefficients on your x's and your y's. So whether or not you are finding your value of x or y, your coefficients on those variables go in the matrix that you're finding the determinant of in your denominator. And they also go on top in one of your columns. Basically, the matrix on top is a copy of the matrix in the denominator, except if you're finding your x's, you replace that first column, which kind of represents your x values, with your constants on the other hand side of your equation, your 5 and 7. And if you're finding your y's, you replace instead the y column with those values for your constants. So we will do one and you can see how it goes. So I'm going to find my determinant of my matrix that's going to go in my denominator first, which comes from my coefficients on my variables. You're going to have 2 times 5 minus -3 times 4 and end up with 22. So when I'm finding my values for x and y, my denominator of my fractions is going to be 22 for both of them. And then to find my value of x, I'm going to take that same matrix I used the determinant of in my denominator and put it in both numerators, but then I'm going to edit it slightly. So to find x, I'm going to replace my x column with 10 and 5, my constants. And to find y, I'm going to replace my second column, my y column, with 10 and 5 instead. Then I'll calculate my determinants and I'll have my values of those two variables. So on x, I've got -15 and 5, 65 over 22. And for y, 10 minus 40 be -30 over 22, which you can reduce. So that's pretty much Cramer's rule. I like it. It's a kind of nice method for solving systems, I feel like, if they are messy for substitution or elimination. So I'll leave B for you, but I want to look at another one that I jotted down here. So if you tried this one, your determinant of your matrix for your denominator is going to be 0. If that happens, that means that it is one of your special cases where either all points on your line are solutions or no solution, so you need to use another method to determine which. Alright, let's do one that's going to challenge you a little bit. So I'm trying to find the values x and y, but this time your coefficients are a and b on a couple of your variables instead of known values. So set it up the same way. When you find your determinant of your matrix that goes in the denominator, a times 1 minus b times 1 is going to be just a minus b. These work the same way, it's just algebraically it's going to get a little bit messier. Good practice for you. Okay, so I'm again going to copy my matrix that I had to start with, but since I'm finding x, I'm going to replace that column with b over a and 1 over b from the right-hand side of my equation. And since I'm finding y's, I'm going to replace that second column with those same values. And then finding my determinant for that b over a minus, if I take b times 1 over b, that's just 1 over a minus b. And for y, if I multiply it, I'll have a over b minus b over a. And then I've got some complex fractions, which we visited before. So I'm going to go ahead and focus on working on those fractions on top by getting a common denominator and then writing it as a single fraction. And if I'm doing that, I'm going to have to multiply by my reciprocal. So I have b minus a over a times 1 over a minus b, which may look like you're done if you just kind of squish that into one fraction multiplying across, but we can actually simplify, because if you remember, you could factor out a -1 and then have actually matching factors of a minus b that divide out to 1, so you'd end up with -1 over a. If you look at the second one, finding y, I'm going to have to multiply by a over a and b over b to get common denominators there. So I'll have a squared minus b squared over ab on top, and then a minus b on bottom. And then if I multiply by my reciprocal, I'm going to have to multiply by 1 over a minus b again. I am running out of space, oh no. We'll make it fit. Okay, so then you can factor a squared minus b squared, because that's a difference of squares, into a minus b times a plus b. And finally, you might notice you have a couple common factors that you can divide out to 1. So you get a plus b over ab for your value of y.